Welcome to this presentation on non-adaptive adversarial face generation. In this work, we introduce a novel method for generating adversarial face images that can fool face recognition systems. This slide illustrates how a deep learning-based FRS operates. As you can see, a face image is passed into a deep neural network feature extractor, which produces a feature vector. All such feature vectors are typically normalized to lie on a unit hypersphere. A comparing algorithm then takes two feature vectors and computes a cosine similarity score. Based on this score, the system makes a decision. Therefore, all face feature vectors from many images are spread on the hypersphere. Moreover, images of the same identity will cluster together on the hypersphere, while different identities are separated by some angular distance. Modern FRSs based on deep learning can be vulnerable to multiple types of attacks. In this paper, we focus adversarial examples. Our goal is producing a face image that looks innocuous but is recognized as another specific person by the system. As shown in the timeline figure on this slide, earlier approaches to attacking FRS often required a source image and used either adversarial perturbations or generative techniques. Therefore, all these prior methods are adaptive, typically requiring an iterative optimization and often a transfer attack setup, meaning they craft adversarial examples using a local surrogate model and then hope the attack transfers to the target system. Our work emerges against this backdrop as a new approach that removes the need for an adaptive, iterative process. This slide summarizes the key contributions of our attack. We outline three major differences: no visible distortions, no source image, and non-adaptiveness. From these innovations, we call ours the first non-adaptive adversarial face generation method. We generate adversarial faces in one shot, making the process more efficient and harder for defenders to detect via iterative query patterns. The first idea is that faces sharing a common attribute, such as gender or race, naturally cluster on an attribute-specific subsphere of the hypersphere. Because of this geometric structure, we can generate an adversarial face simply by projecting onto that subsphere, without any iterative optimization. As you can see, feature vectors span on such subspheres inverse to faces that exhibit target attribute. The second idea is that the basis that spans these attribute subspheres is consistently preserved across different FRSs. This means we only need a small number of non-adaptive queries to extract meaningful output information from a target system, such as the commercial APIs. As a result, we can generate adversarial faces that successfully deceive real-world services with very few queries and without iterative adaptation. In the whitebox setting, we first estimate the basis of the target attribute subsphere, for example by applying PCA to feature vectors that share the desired attribute. We then project a feature vector onto this subsphere using that basis, and reconstruct the image using an inversion model such as Arc2 face. This allows us to generate an adversarial face in a single step, without any iterative optimization. In the black box setting, the universal basis hypothesis allows us to infer a feature vector in the local space using only the score information returned by the target system. Once the feature is estimated, we simply project it onto the target attribute subsphere, just as in the whitebox case, and reconstruct the adversarial face with an inverse model. The score matrix S here is only a mathematical tool to correct the basis alignment error. We do not go into its details due to time. Our experimental setting includes multiple target datasets in both open source and commercial systems, including the AWS and Tencent APIs. We also use one local model together with two inverse models for reconstruction. As shown in both tables, even when attacking fully black box commercial systems such as AWS and Tencent, our method achieves high success rates across genders and ethnic groups with only 100 score queries. This demonstrates both the practicality and the query efficiency of our non-adaptive approach. As shown here, prior diffusion-based attacks often introduce visible distortions in the generated faces, making them noticeably unrealistic. In contrast, our method produces clean and natural-looking faces while also achieving significantly higher attack success rates across all attribute groups. Finally, we want to emphasize that the goal of this work is to uncover structural vulnerabilities in face recognition systems, so that we can better understand them and ultimately strengthen them. We also provide practical defense directions in the paper, and we hope that this research contributes to building safer and more reliable face recognition systems in the future. Thank you for your attention.